day 22 of Honors Precalculus. Today we're going to continue talking about parametric equations. And in this case, we're going to be throwing a ball into the air, and it's going to be the height of the ball. The height of the ball is going to be governed by this equation. V sub 0, so this is actually pronounced V sub naught, N-A-U-G-H-T. V sub naught is the initial velocity, and H naught is the initial height. And this is what happens to the height of the ball when gravity is in play. So you throw it, and that's what happens. So the initial velocity and the initial height. And remember, this formula only gives you the height of the ball as a function of time. So let's suppose we throw the ball with an initial velocity v naught and initial height h naught, and at a certain angle. So what it means by a certain angle is we've thrown it, and at the instant we've thrown it, this angle right there is our theta value right there, the initial angle we've thrown it at. So it actually kind of be tangent like this. So the initial angle is actually right there, because gravity starts working on it and pulling the ball down. Okay, so what we're going to do is it asks us to write the path of the ball by a parametric equation. What is that going to look like? Well, initially, this is important here, you have a triangle where the initial, again, you have initial velocity of v naught. You know that this angle, if that angle is theta right there, the triangle that it forms, and it'll go the initial triangle like this, the initial triangle right there, this side of the triangle will be v naught sine of theta, and this will be v naught cosine of theta. And you should remember that because sine is opposite over hypotenuse. So the initial velocity, this is at the initial velocity, is the length of that vector right there. So what does that mean? It means that we can write our equation a little differently. So we know the height is going to be negative 16t squared, but then what happens with respect to theta? Well, if we go back to our original equation, it originally was v naught t right there, right? V naught t. So what we're going to do instead is we're going to write it as plus v naught sine theta times t, because this distance is going to change over time, specifically with relation to how the theta starts. But you started at an initial height. The x-coordinate is just going to be v naught cosine theta times t, because as time goes on, this distance changes, and this is the x-coordinate. That is the x-coordinate. And the reason this isn't just a straight line going up with the initial velocity is because of gravity. It's pulling it downward. So basically what we've done is we've written a generalized parametric equation that you can use to find where this particle is, where this ball is, from an initial height, an initial velocity, and an initial angle measure. All of those things could be changed. You could throw the ball a different force from a different height at a different angle, and then this would govern where the ball is. So let's use that. Ralph hits a baseball 3 feet above the ground, so that tells us that our initial height, and I'll use not the highlighter, our initial height is 3, so h naught is 3 feet, that's where this comes from, with an initial velocity of, so v naught is 150 feet per second at an angle, let's say an angle, we can call it alpha or theta, equals 18 degrees with the horizontal. That means, with the horizontal means it's this. The positive x-axis is the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? So from above, the generalized parametric, we know that x is going to be v naught, which is 150 cosine of 18 degrees times t. That's from above. And y is equal to negative 16t squared plus the initial velocity sine of 18 degrees t plus 3, the initial h naught. So that's h naught right there. There's our alpha value, and there is our v naught. So what's going to happen here? Well, you want to know, does it clear a fence 400 feet away? Sorry, will the ball clear a 20-foot fence that is 400 feet away? So you can ask the question, at what time is it 400 feet away? So it's 400 feet away. That's the x distance, 400. So when does this equal 150 cosine 18 degrees t? This tells you when it's 400 feet away. So if you do that, t is equal to 400 over 150 cosine 18 degrees. If you do this out, you get 2.804. So what that means, at 2.804 seconds after being hit, the ball is 400 feet away. Now you want to know, what's the height when it's this time? What's the height when it's this time? So the height when it's that time is y equals negative 16 times 2.804 squared. We're taking this number right here and we're plugging it in for t. We've got to keep going. Plus 150 sine of 18 degrees, and make sure you're in degrees, times 2.804, because that's the t, plus 3. So this will be the height at 2.8 seconds, which is when it's 400 feet away. When you do this out on your calculator, you end up with 7.178 feet. So will it clear a 20-foot fence? It will not. 400 feet away, it'll only be 7.178 feet off the ground. So what you can do is you can change the initial angle, do everything we just did, but with 19 degrees and then with 20 degrees, and see what happens graphically. So theoretically, we got something like this. So maybe is it going to be shorter and higher or up? What's going to happen? You should test that to see if it's going to clear the fence. If it's going to clear the fence. So what's interesting here is what happens if there's a 10 feet per second wind coming at the hitter? So before, our x was, before we did anything, it was 150 cosine of 18 degrees times t, and our y was negative 16t squared plus 150 sine of 18 plus 3. What does this do? 10 feet a second coming at the hitter. That means it's going to change this by negative 10. So this right here adds a negative 10 right there. That's all it does. So it makes it go slower going forward, but it doesn't change the overall height. It doesn't change the overall height. So just to recap, what you really need to memorize from this are these two equations right here. These two for a particle or ball or whatever you want to call it that is launched from an initial height of h naught, initial velocity, of v naught. And then this will be the vertical position, and this will be the horizontal position. And it's defined in terms of those three things: initial velocity, the initial angle, and the initial height.